Hello, so this is a revision video for AP Chemistry 3.4, Ideal Gas Law. This is a revision video, so only the essential information is covered. For more detailed explanations and full video lessons, please check the links in the description below. An ideal gas is a simplified model used in chemistry and physics to help us understand and calculate gas behavior. The model itself is based on a set of assumptions. These assumptions enable us to consider that only temperature, pressure, and moles of a gas determine the volume it occupies, meaning we can ignore the type of gas that it is. Key assumptions include that particles are in constant random motion. They move freely in straight lines until they collide with other particles or walls of the container they are in. The volume of individual gas particles is negligible. The size of the gas particles is so small that their total volume is effectively zero compared to the container size they are in. No intermolecular forces exist. There are no attractions or repulsions between gas particles. They don't interact except during collisions. All collisions are elastic. When gas particles collide, they don't lose kinetic energy, and the total kinetic energy before and after a collision is the same. Temperature is related to average kinetic energy. The higher the temperature, the faster the particles move. All particles have different kinetic energies, but the average increases with temperature. Now, these are assumptions, and although no gas is truly ideal and doesn't follow these assumptions perfectly, most gases do behave like this under most everyday and normal conditions, especially at a high temperature and low pressure. However, at low temperatures and high pressures, real gases deviate from these assumptions. This is because at high pressures, the actual space that gas particles occupy becomes significant. We can't ignore it, meaning their individual volume is no longer negligible. And at low temperatures, attractive intermolecular forces between the gas particles become significant, making gas particles more likely to stick together. However, these are quite extreme conditions for the exceptions. For nearly all everyday chemistry, real gases follow ideal gas behavior nearly perfectly. Modeling gases as ideal gases enables us to use the ideal gas law. The ideal gas law is given as PV equals nRT, with P being pressure, V being volume, N being moles, R being the universal gas constant, and T being temperature. Pay really careful attention to the units when using the ideal gas law. In mixtures of gases, each gas contributes to the total pressure independently. This is called Dalton's law of partial pressures, where the total pressure, P total, equals the partial pressures of all gases present added together. The mole fraction of a gas is the moles of a particular gas divided by the total moles of all gas. And the partial pressure of a gas equals its mole fraction times the total pressure of the system. Notice here how an ideal gas assumption is really important, because we're treating the different types of gas in the system identically. There are several graphs for gas relationships that you need to be comfortable with at this level. Pressure versus volume at a constant temperature gives an inverse relationship, Boyle's law, whereas the volume increases, pressure decreases. Notice if you make the x-axis 1 over volume, you get a straight upwards line, with pressure being directly proportional to 1 over volume. Volume versus temperature at a constant pressure gives a direct relationship, Charles's law. As temperature increases, volume increases. Pressure versus temperature at constant volume also gives a direct relationship, Gay-Lussac's law. As temperature increases, pressure increases. Volume against moles of gas at a constant temperature and pressure also gives a direct relationship, Avogadro's law, where more moles equals a greater volume of gas. These relationships can all be explained by kinetic molecular theory, which models gas behavior at the particle level and is covered in 3.5, kinetic molecular theory. Exam tips here. If a question involves gas mixtures, always calculate mole fractions before partial pressures, otherwise you're going to run into difficulty. Don't forget to convert Celsius to Kelvin when using the ideal gas law, and always check the units being used for R, the universal gas constant.